Hi there, welcome back to this channel. In this video, we are going to begin our series on organic chemistry. I will enjoin you first to see this series from beginning to the end in order to have a good background or good grasp, overall grasp of organic chemistry. Now, we are going to treat every topic in section as they are associated with each other. Now, we are going to begin first here with a brief history, and then we are going to graduate to hybridization, why organic chemistry is studied, hybridization, bond polarization, chemical bonding, then bond polarization, bond fission. Bond polarization will lead us to the effects of bond polarization, all those inductive effects, electromeric, mesomeric resonance, and all of that. Then we will now see we'll see isomerism. I have already made videos on some of those topics, so I'm going to link them in the description. But one other thing I'm going to enjoin you to do is any part of organic chemistry that you want me to specifically explain in detail, drop them in the comment section. Drop them in the comment section. Any parts that you want me to specifically explain, especially naming for many of you. So I have made a video where I named about 50 molecules. I'm going to link it in the description as well. So with that said, let's begin the video already. So let's begin with a brief history. Now, historically, the name organic chemistry was actually given by Berzelius in 1807. Okay, so Berzelius in 1807 gave the name organic chemistry to the field of chemistry that was devoted to studying compounds of carbon. But actually, the name did not just come about. It came about because of pre-discoveries that preceded this period, which were those of Ruel, who in 1773 discovered urea, synthesized urea from urine, which is a product of an animal waste, right? Scaly, who discovered chlorine, had already also discovered between 1742 to 1786, he discovered tartaric acid, which is the chief component in grape, and he also discovered citric acid from lemon and malic acid from apple. Okay, now because it was such that these organic compounds were discovered from living tissues, living things. So there came an idea that surrounded the fact that organic compounds could only be synthesized, could only be biosynthesized. That is, we can only derive them from living tissues. All right, and because of that, they suggested that there was something which led to the biosynthesis of organic compounds within living tissues, which they tagged the vital force. Now you will soon come to know that at the end of the day that the vital force idea was abolished because it was proven to be wrong. Now the reason why the vital force theory came was that initially at that time scientists did not believe that organic compounds could be synthesized from non-living tissues, okay, or non-living things. But in 1828, this was when the turnaround came. Frederick Waller was the first person to synthesize the same urea from ammonium cyanide. So what did he do? What he basically did was to boil ammonium cyanide to a very high temperature, and he discovered that he was able to synthesize urea. And if you see the chemical formula of ammonium cyanide actually, if you see this chemical formula, you're going to see that this is basically what you have in urea as well. All of these chemical atoms, all of these atoms are composed in urea. So by boiling, he discovered that there was a rearrangement. What happened was just a rearrangement of the atoms that make up the ammonium cyanide. Okay, and he was able to synthesize urea. And that's the chemical formula of urea, which he was able to synthesize. So by the end, at the end of his experiment, the vital force theory, or the people that held the ideology of the vital force, became to, the idea became, it began to stagger, it began to shake. Then again, someone else, I can't remember his name right now, also was able to, that's Kolbe, the Kolbe process. I'm going to take us through it. Kolbe process. I'm going to take us through many chemical reactions after we have covered a whole lot in this series. So the Kolbe was able to synthesize acetic acid from its component atoms, its component elements. Acetic acid. He was able to synthesize it from its component atoms, and because of that, because of these again, the vital force theory was abolished. Okay. So now, why specifically was this organic chemistry, why was it given a separate field? Okay, now there are a number of reasons that made scientists to consider organic chemistry as a separate field in chemistry. Okay, and one of it is the fact that there's a large amount of organic compounds that can be. Okay, let me list the reasons. Let me pause it. All right, so now some of the reasons why we said the organic chemistry was given a separate field include the large number of compounds that carbon that is able to be formed by carbon by organic compounds. Okay, organic compounds are so numerous that in fact about more than 4 million compounds have been synthesized in the laboratory, and it is believed that many more such compounds still exist. Many more compounds that have not been synthesized still exist. Exactly. So, but if you look at inorganic chemistry, about just a little bit above 50,000 compounds have been Now, what are the reasons why we said that the organic chemistry was given a separate field? Number one is the large number of compounds that can be formed with carbon. Okay, now the organic compounds are so numerous that right about now we have more than 4 million atoms, 4 million compounds that have been synthesized in the laboratory, and it is still suggested that or it is believed, that there are many more organic compounds that have not even been synthesized or discovered at all. Okay, so but in the field of inorganic chemistry, you are going to see that only a few such compounds, or relatively few, would I say, because only about 50,000 or just a little bit above 50,000 compounds have been synthesized in the laboratory that belong to the inorganic compounds. Okay, so the relatively large number of compounds that can be formed makes it plausible to give organic chemistry a separate field. The next is it is built of relatively few elements. The number of elements that you need, in fact, the relatively few and predictable elements. Okay, you can predict the elements the number of elements are few. But you see, in inorganic chemistry, the compounds that are formed, including salts, which are the three basic classifications, salt, base, and acids, usually can be formed from any of the 118 elements on the periodic table. Okay, so that is very large. That is very hard to predict. But with organic chemistry, you can predict that carbon is definitely going to be there, part of the compound. Hydrogen, carbon, which is the chief component, hydrogen, oxygen, nitrogen, sulfur, okay, oxygen, nitrogen, sulfur, phosphorus, and the halogens. Okay, so these are the major components of the organic compounds, and they are just these few numbers that you can see, except in some cases where you can have maybe soaps or other things where you can have metals and all those things and other components, other atoms attached. But at the end of the day, it is relatively few number of elements that you see, chiefly carbon, and then many of the times you see just this one that I have listed. Okay. Now the next one is the functional group, which is the basis for the classification. Okay, there are just three classifications in inorganic compounds. We have the acids, the bases, and the salts. But in inorganic compounds, they are classified based on their functional group, so that compounds that have double bond will be alkenes, single bond or saturated alkanes, compounds that have OH as a functional group, alcohols, ones that have COH, carboxylic acid, ones that have NH2, amines. These functional groups help us to classify them, okay, and that makes this organic compound, organic chemistry relatively easy, and organic compounds easier to identify, easy to describe, easy to even predict their reactivity. Okay, then the molecules are formed by covalent bonding. Yes, that is it. In inorganic compounds, we are going to see that there are many different types of bonding that we have treated. Would link the video in the description. But you see, the organic compound is chiefly, the molecules are basically formed by what? Covalent bonding. Now, what is covalent bonding? A type of bonding. We are going to see it. I'm going to discuss it better later. So a covalent bonding is just where two atoms are sharing electrons. Okay. So since the molecules are formed by covalent bonding, you can also predict what the molecules, how can you do with that? Covalent bonding. Basically, you know that it is formed by covalent bonding, and that is statutory for organic compounds. But in inorganic compound, you have ionic bonding or electrovalent bonding, covalent bonding as well. You can also have coordinate covalent bond or dative bond. Hydrogen bond. It is van der Waals forces and all of those things. There are many types of bonding that you have in inorganic chemistry, but in organic chemistry is chiefly covalent bonding. Then the other one is the unique characteristics of carbon, and the unique characteristics simply are the valency, the tetravalency of carbon, and its ability to catenate. There are also other compounds that can catenate, but it has been found that carbon is the the one that has the that is most studied and has the most shows a high degree of catenation. First, what is catenation? Is the ability of carbon to form straight chain, branch chain, or ring structures with itself and other compounds. Okay, and that usually range from small to gigantic molecules. Exactly. And those gigantic molecules are also consistent. Okay, so the point is that catenation and its tetravalency are two unique characteristics that carbon has that makes it to hold a separate field. And then we have isomerization. I have covered isomerism about twice. I will link those two videos in the description, so make sure you see that video. It's just the ability of carbon compounds to be able to, or organic compounds, to be able to form different, to have different structural formula, but may have the same molecular formula. Okay, so you will have something that has the same number of atoms, the same components of atoms, but will have different structures. So that's isomerism, and that's basically structural isomerism. That's not the only thing in isomerism. But physical states also, the physical states of organic compounds also help us to be able to give them a separate field of study. Then we have the pattern of solubility. Usually, compounds that are formed by covalent bonding are usually they are insoluble in water or in polar solvents. Usually because this bond is mostly non-polar bond. Exactly. Doesn't mean that there is no polarity in covalent bonding, but it is mostly non-polar. So because of that, the pattern of solubility of organic compound is such that they are soluble only in organic solvents. Example of organic solvents include benzene, ether, chloroform. So they are soluble in only these guys, but insoluble in inorganic insoluble in polar solvents like water. So they are not soluble in water. While inorganic compounds mostly are soluble in water, polar solvents, and insoluble in organic solvents. Okay. Now, electrical conductivity. So compounds that are formed by covalent bonding, which we know of organic compounds, are usually unable to conduct electricity. So organic compounds are chiefly non-conductors, while inorganic compounds are conductors of electricity. Then we have the low melting and boiling points. There is almost no salt of inorganic compound that can be melted at 700 degrees, at less than this. Most of them are usually have melting points that are above 700 degrees Celsius. But you can imagine for for organic compounds rather, they are mostly melted at about less than 300 degrees Celsius. Most of the organic compounds that we have. So that is another unique characteristic. And then another is combustibility. Organic compounds are generally combustible. They're generally combustible. Combustion reaction simply means reaction with oxygen. Exactly. That is the way we write it theoretically. So most organic compounds are combustible, but inorganic compounds, it's not all of them that can undergo combustion reaction. The nature of the chemical reaction. Okay, so they exhibit a diverse range of chemical reactions, which of course, if you follow a particular family or series, you can predict each case, but it is different and diverse from the array of reactions that we have with inorganic compounds. Okay, so that said, let's now talk about the tetravalency of carbon. Now, before we talk about the tetravalency of carbon, let's first talk about the atomic structure of carbon. Okay, so structure atomically, carbon atomically, the atomic structure. You know, an atom has protons, neutrons, and electrons, right? Protons are the positive charges that are together with the neutron in the nucleus, and electrons are the negative charges that form a cloud of orbit around the nucleus here. Okay, now that said, we know that the number of protons is equal to the number of electrons, and a chemical reaction occurs when there is either a sharing or a donation of an atom, okay, of an electron rather. Now, in this case, for organic compounds, it is compounds are formed mostly by covalent bonding. Okay, so there are two types of bonding. We have the bonding. We have the covalent bond and the electrovalent or ionic bond. Now, the covalent bond, the word co means together, right? So it means that there is a sharing of electron. It suggests a sharing of electrons between two compounds, okay? Now, while the electrovalent bonding is one where there is a transfer of electron from one atom to the other. I've explained that before, so I'm going to link the video in the description as well. So there's a transfer of electron from one atom to the other. Now, in this covalent bonding, usually atoms that engage in covalent bonding are atoms of elements that have the same or almost equal electronegativity. So which means that we have to talk about electronegativity. But before that, just to remind us of what covalent bonding is. So what we'll see with covalent bonds, covalent compounds rather, is, for example, let's consider methane, since we are already dealing with organic compound. So with methane, you are going to see that carbon is going to share, carbon exhibits tetravalency, so it's going to share one electron in each case first. The bond we draw here, anytime we draw a bond, you should consider it as two electrons. The two ends there are two electrons that are connected together. Is that clear? So a bond represents two electrons, okay? So one electron that is here is going to belong to carbon, and the one that is here is going to belong to the atom that is bonded to it, okay? So carbon exhibits tetravalency. We're going to discuss why soon. But this is to show you that this guy is going to be bonded with one hydrogen. So there are two bonds, two electrons rather, between carbon and hydrogen. There are two electrons between this carbon and this hydrogen, and there are other two electrons between this carbon and this hydrogen, and there's another two electrons between this carbon and this hydrogen. So basically, these four electrons are the ones that are owned by the carbon, okay? Then the remaining four are contributed by the hydrogens individually, and both of them are going to share in order to attain stability, because at the end of the day, that's the essence of this bonding, to attain stability. So this is covalent bonding in a nutshell. Now, I mentioned the word electronegativity the other time, just now. Electronegativity. Now, electronegativity is basically the ability of one atom to draw electron density to itself, okay? To draw electron density to itself. Now, and non-metals are usually electrovalent, okay? So they usually have a high capacity to draw electrons to themselves. By the time I want to discuss it in full, I'm going to discuss the Pauling scale. Is that okay? Now let's talk about tetravalency of carbon now and hybridization. So when you look at the orbital diagram of an atom, of a carbon atom, you are going to see that it suggests that a carbon atom should actually be divalent. So why is a carbon tetravalent? That's what we want to explain. Okay, so carbon has 6 electrons, and if it has 6 electrons, what that means is that it's going to have 2 electrons in the 1s orbital, so the electron configuration will be 1s2, then we'll have 2s2, then we'll have 2p2. Okay, so actually what you should see with carbon is 1s2 with the electrons in opposite spin, then 2s2, then 1 and 1, following Horn's rule. Okay, now these 3, since p orbital is degenerate, is going to be 2px, 2py, and 2pz. Okay, remember that the p orbital is degenerate into x, y, and z. Okay, now based on this orbital structure, this guy is supposed to be divalent. So how does it exhibit tetravalency? Okay, now several ideas have been postulated, and one of which was the structure of methane basically was explained by Van Libel and Van Hoff. Okay, and they were able to explain why methane had its tetrahedral structure, and why that same tetrahedral structure is shown in all alkane families. Okay, I think they basically use methane and methane to explain that, and I'm going to do justice to that now. So they used the concept known as hybridization to explain hybridization. Okay, now what is hybridization? Hybridization is simply a mixing or a merging of atomic orbitals so a mixing or a merging of atomic orbitals that have nearly equal energy. Okay, because one of the criteria for there are basically 2 criteria. One of them is that the orbitals that are to be mixed must have have equal energy or nearly equal energy. So that is why you are going to see that it is the energy level 2 orbitals that are going to be mixed. Energy level 2, the orbitals in energy level 2 are the ones that are going to be mixed in this concept of hybridization that is going to happen here. Okay, so we're going to have equal energy or nearly equal energy in order to redistribute their atoms and their electrons rather. Okay, so hybridization simply means mixing the mixing of atomic orbitals that have nearly equal energy in order for them to redistribute their electrons. Okay, now usually this hybridization will alter the shape and orientation or conformation of that particular orbital, because the new orbital that will be formed will be known as a hybrid. So that hybrid is not going to have exactly equal shape or configuration with the 2 initial orbitals that were mixed. It's going to reorient itself, albeit it will still follow the protocol of having maximum of 2 electrons in each orbital, and also the 2 orbitals, it will be composed or comprised of the 2 orbitals that made it up. Okay, so what was discovered with methane and ethane and other alkanes is what we call the sp3 hybridization. sp3 hybridization. And what does sp3 hybridization mean? sp3 hybridization means 1s character. It means an hybridization that consists of 1s character and 3p characters. Okay, so how did this happen? So it happens when, or how does this happen? It happens when carbon wants to engage in chemical bonding with other compounds. What it does is that it first gets excited, so it undergoes excitation. So during that excitation state, one of these electrons here is going to be promoted to this 2pz orbital. So on promotion of this guy to the 2pz orbital, we are going to have a new configuration for our guy, and it becomes 1s2, 1s2, then we'll have 1, 2, 3, 4 at a higher energy. And you notice that I'm not drawing them the same energy level, because this energy level 1 is going to be lower than energy level 2. So I'm even supposed to draw it lower around here. So this is going to be 1s2, and you'll see the opposite spins. Then we're going to have the 2s. We now have only one electron, because this electron will be promoted to this place. Then the 2p sub x is going to have one electron as it initially had. The 2p sub y is going to have one electron, and the 2p sub z is also going to have one electron now. Initially, the 2p z was without electron. So, but when carbon wants to engage in chemical bonding, it will get excited, and in that excited state, is going to promote one electron to that point, which result in an increase in its energy or the stability. Is that clear? So it becomes more unstable and, or more reactive. Does that make sense? Okay, so when there is a promotion of that electron to that 2pz electron, to that 2pz suborbital, what happens is that there is an increase in the energy of that carbon. Okay, so the mixing that takes place here, if the mixing now happens that they are merged together to form orbitals, then this is the way the orbital formation happens. So for the s character, remember that the shape of s orbital is actually spherical, and the shape of p orbital is dumbbell, right? So but at the end of the day, on mixing of each of these orbitals, we are going to get a new orbital called an hybrid, that will have a tiny lobe and a big lobe, a small lobe and a big lobe. So this is the hybrid that has been formed. Okay, so usually when we are drawing, we draw the bigger lobe to show we show only the bigger lobe in the electrons, in the compound formation. To show the compound structure that has been formed, we show only the bigger lobe. And notice that this dominating orbital, the dominating orbital is the one that has the larger share in this lobe. Does that make sense? That is, the dominating, or the electrons, the chief orbital is going to be the one that will take this larger lobe. And at the end of the day, it means that electrons will be found on the larger lobe. Okay. Now, so here is what happens with methane. So once with methane, 1s orbital and 3p orbitals are going to mix. Okay, so once they undergo mixing, then we are going to form four sp3 orbitals. We are going to form what? 4 sp3 orbitals, which essentializes 4 bonds or tetravalency for carbon. I hope that is clear. It's going to form on, after that excitation, if the 3 orbitals mix, if the 1, 2, 3, 4 orbitals mix together, then you are going to see 4 sp3 orbitals formed in the process. Okay? Now, on formation of that sp3 orbital, what follows? First, let's consider the geometry, the shape. Okay, now the shape of the sp3 hybridization follows the Vesper theorem. Now, if you want me to explain the Vesper theorem, make sure if you want to release another video on Vesper theorem, you can suggest in the comment section. So the Vesper theorem which is valence shell electron pair repulsion. Valence, let me write that. So valence shell electron, I'm not discussing it here exactly, repulsion, because I assume you should have learned it before in coordination chemistry. Okay, so now according to this Westphal theorem, we are able to tell the geometry or shape of this guy, of the methane that will be formed, the 4 sp3 orbitals that will be formed. Now, in methane, the geometry they maintain, or just as according to Westphal theorem, they must maintain a geometry that will separate or keep the electrons apart from each other as far as possible, because this theory maintains that electrons, and since they have negative charges, and electrostatically we know that negative charges repel each other. So because of that, those electron pairs are going to repel themselves as far as possible. Okay, so this gives our methane a 3D geometry that looks something like this. So we're going to, I told you that we're going to be showing only the larger lobe. So we're going to find methane to have something like this. So this is going to be our carbon. So we're going to have a molecule that looks, a shape that looks like this. Let me redraw that. So we have our carbon, we have the large loop here, we have one loop here, we have one loop here, we have one loop here. Okay, so this is going to be the molecule, the shape of our methane. So in line notation, we are going to have what looks like this. Okay, so that the bond angle between each one is going to be 109.5 degrees or 109 degrees 28 minutes in radians. Okay, then so from here to here, 109.5 degrees, 109.5 degrees, 109.5 degrees, 109.5 degrees. Okay, but this is going to be a 3D molecule because they are going to orient themselves as far away from each other as possible. Okay, that's what we see with the methane. Okay, so far we have said it's sp3 hybridized and it's going to form, this shape is called a tetrahedral shape. The shape that is formed is called a tetrahedral shape or a tetrahedral geometry. So when methane now wants to bond with hydrogen, for example, when carbon wants to bond with hydrogen to form methane, for example, what now happens is this. You know already that hydrogen has only one electron. So let's say our hydrogen has only one electron. So this one electron, and this guy already has only one electron after that excitation takes place. So one electron on each of the far end of the tetrahedron. So what happens is that this guy is going to come and form a bond with this guy. And after the bond is formed, you will now have 2 electrons here, one belonging to the hydrogen, the other belonging to carbon. Then another hydrogen will come, another hydrogen, and another hydrogen, and another hydrogen. Okay, so they are going to form, and then we have hydrogen here, we have the hydrogen. So the 4 hydrogens are going to orient themselves around the 4 ends of this tetrahedron that is formed. Okay, so then the bond that is formed is called a sigma bond. Sigma bond. Okay, the way it is drawn is somewhat like this, here, something like this. Okay, So sigma bond, and a sigma bond is a bond that allows for symmetrical rotation, okay, about its axis. It allows for free rotation about its axis. So, and it is formed in a single bond. Is that okay? It is formed in a single bond. So throughout here, you are going to see single bonds, okay, in the methane molecule. If it was an ethane molecule, what you would see is almost the same, but the thing is that the carbon, there are two carbons that are going to form head-on overlaps, and this forms head-on overlaps between the hydrogen and this guy, and these two carbons are going to form head-on overlaps as well. So we have two electrons here that they are sharing, then the other electrons orient themselves in the other way. Okay, then hydrogen will now bond at the vertices. Okay, so this is going to be what? Methane, that will look somewhat like this, yeah? So methane is going to look, ethane is going to look somewhat like this. So at the end of the day, we're going to see that they form 4 bonds, sigma bonds all through that has, and sigma bond is the strongest bond, is the strongest covalent bond, and usually has a longer length. It is longer with a length of about 1.54 nanometers. But if you see the pi bond has a lower, is it 1.54? I can't really remember, but it is longer than the pi bond. That's the point. It is longer than the pi bond. Let me just clean this because I'm not so sure. All right, but the methane, so this the sp3 hybridized orbital is going to have all of these characteristics. Okay, is there any other thing I've not discussed? We have discussed the geometry, the shape, and okay, so in characteristics we're going to have, so all of these bonds that you're seeing here are all sp3. So this sp3 bond, sp3 hybridized, sp3 hybridized, sp3 hybridized, sp3 hybridized, sp3 hybridized, and you would think that the s orbital here, this is going to be between ss orbital. Okay, now you think that they are different in geometry. All of them are going to have this shape that I drew the other time. All of them are going to have that shape. Okay, so I think I've pretty much done justice to sp3 hybridized. Let's go to the second, which is sp2 hybridization. By the way, I think I'm using the biggest duster on the internet. Okay, so we have sp2 hybridized or hybridization. Now, what is sp2 hybridization? sp2 hybridization is a case where after the promotion of an electron, only 3 of the orbitals are actually combined together. 2 of the p and 1 s orbital. Okay, so at the end of the day, we're going to have only 1 s and 2 p orbitals. Okay, so they are going to, this one is going to, so it means that the s is going to contribute about 33.3% in character, while this one is going to contribute about 66.6% in character. Then what happens here is this. It means that there's going to be a third orbital, the pz orbital, the 2pz orbital, that is not going to be what? Hybridized. So that unhybridized orbital is going to give rise to a special form of bond, because electrons will also stay there. And if electrons are there, it means that they will be susceptible to attack again, right? So because of that, those 2 orbitals are going to merge with themselves laterally or sideways merging. Is that okay? Sideways overlapping rather. Sideways overlapping of each of themselves. So you are going to see of each other rather. So you're going to see in this case there's going to be each of these guys will give you a pi bond. So the sp2 will give you a sigma bond, while the sp2 is going to give you a while the last one is going to give you a pi bond. Okay, let me put that in diagram. Let me show that diagrammatically so that you understand what I'm talking about. So let's use, that's why there is no methane. So this bond can only, sp2 hybridization can only occur with compounds that have double bonds. Okay, so and the double bond must occur between two carbon atoms. First, let's talk about the geometry. So it looks pretty much like the sp3 hybrid, only that it is larger. The lobe in this one is larger. So you're going to see what looks like this. So if this is the carbon or this is the nucleus, so you're going to see what looks like this. So this one is going to have its own smaller lobe here. So, and each of these orient themselves about now, this is what I wanted to also explain. You see, the s orbital is merging with only the x and the y orbital. So because of that reason, the molecule is going to exist only on the xy plane. So this is going to be a two-dimensional shape molecule. Does that make sense to you now? So it's going to exist on only the two, the y and the z plane, okay, but not on the z, y and the x plane, but not on the z plane, okay. So the shape that will be formed, because they are going to exist, and they are going to, you know, also push themselves as far away as possible, so that they are going to have about 120 degrees distance away from each other by the Vesper theory again. So they are going to have 120 degrees. They are going to be about 120 degrees away from each other. Now, and the orbitals that want to form bond with them, another compound atom that want to form bond with them will come and attach themselves to these three ends of the trigon. Now, the shape that is formed is a trigonal planar shape. Now, it is planar because it's going to be on a particular, it's going to be planar on two axes, okay, or triangular planar. I hope that makes sense. Trigonal planar or triangular planar. All right. So if this guy wanted to form bond with another compound, so here's what it does or how it does it. The shape of this guy is going to look the shape of ethene, for example. Ethene is going to look something like this. We're going to have our three lobes. Our first lobe from the carbon that is going to, have head-on overlap with the lobe of this guy for this carbon, and the third lobe is going to orient itself so that they are at 120 degrees, like I said initially. Then we now have, okay, for this guy also we're gonna have what looks like this. Okay, then we now have remember that only the x, the px and the py, only those two were, hybridized here. So the pz that is unhybridized, so on the z plane, this is going to be on the z plane. So I have rotated what I'm drawing here. I've rotated it so that the z plane is going to fall up and down like this. It's on the z plane, okay, but I'm drawing it in this shape so that you see that it has fallen up and down. Then this guy is also going to be like this. So this is the pz of this carbon, and this is the pz of this our own carbon here. So what happens is that although there is head-on overlap here of these two carbons, then there is now lateral overlap. These two will be they will form a lateral overlap. What happens is that they actually, they were standing like this before, then they will now bond together. So they are going to form what is called the pi bond. So these two are one because they are formed from one PZ. Is that okay? It is the same PZ. This PZ forms one bond. So these two you are seeing here refers to the pi bond. Then this one you see here is the sigma bond. While here, then we now have the hydrogen is going to attach itself here. Hydrogen will attach itself here. Hydrogen will attach itself here. Hydrogen will attach itself here. Okay, so then we now have, this is the shape of our ethene molecule. This is ethene, CH2CH2. All right, so this is how it is formed geometrically. Then let's look at, so we have seen the bond angle, and it gives rise to pi bond. Pi bond is weak. Number one, pi bond is weak. The pi bond that is formed is weak. Okay, so that's why it makes ethene susceptible to attack, and it is easy to actually break the pi bond. Okay, it's easy to break the pi bond. Then apart from that, the shape formed is trigonal planar, and what else again? I guess that's basically it. If there's any other thing I have to talk about, I'll come back and talk about it. So let's look at the last one, which is the sp hybridization. The sp hybridization. Now with sp hybridization, what this tells you is that after the promotion that has happened here, then these two will not mix. Only these two will mix. Okay, so if the two mix, then you are going to form sp hybridization everywhere. And what that means here, just like we formed sp2, 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 here we're going to form sp hybridization everywhere too. And what that means is that there's going to be 50-50% contribution from S and P. So we have 50% S character, 50% P character. And remember, only the X, PX is combined here. So it means that you're going to have your compound, they formed on only the X plane. So this guy is our hybrid, and this one, so this is our hybrid orbital, which comes from the S shape and the dumbbell shape of the P orbital. Okay, so now how do they form geometrically? So by the time carbon now wants to form compound with another carbon to form ethine. Now how does it happen? The first carbon will come with its orbital, and then this other one will also come with its orbital. Okay, and then there's going to be head-on overlap here, right? Head-on overlap. So they share electron. Then what you will now see is that on the y-axis, remember the py did not hybridize. The py did not join the hybridization. They are going to form. So this one is going to form a sigma bond, while the two here are going to form just like here. They're going to form the first pi bond 1. Then we will now see another plane, the z plane. We're going to see another plane here, where there is going to be interaction again, or lateral overlaps. Remember I said lateral overlap or sideways overlap. Okay, so lateral overlap of sideways, that's what it means. Like the two orbitals px, py, they are going to overlap this way. Does that make sense? So this is one bond. Then apart from the head-on overlap that happened with the S, with the two carbon atoms rather, then there's another on the z plane now, on the z plane into and out of the board, there's also going to be what? Lateral overlap. Does that make sense? Just like happened with what? With the py. So then because of that, what you are going to see is a shape, a molecule that is linear. A molecule that is what? Linear. Okay, to represent this in diagram, how do we even represent? We usually just draw a straight line, a curve here and a curve here. This curve here represents the pi bond, this one represents the sigma, this one also represents the second pi. Is that okay? So this will be pi bond 2, pi bond 1, pi bond 2, pi bond 1, pi bond 2, pi bond 1. Okay, so this is the way the ethine or sp1 hybridized molecule is formed. So then the shape is linear. The bond angle, once is a straight line, angle on a straight line is what? 180 ground north degrees rather. Then, so that's that. That's that. Now let's now talk about, we've talked about hybridization. Let's talk about, we've talked about bonding, okay, now let's talk a little bit more about electronegativity. So that we'll now talk about bond breakage or cleavage, bond cleavage or bond fission. Those are the names we use to refer to it, to that phenomenon. So let's talk about electronegativity. Now, what is electronegativity? We know that atoms have different capacities to draw electrons to each other. So when there is a bond between two compounds, two or more atoms, now the tendency to draw electrons towards each other differ. Okay, it's just like sharing something with your friend. Now, even if it was your friend that you were born in the same month, I'm just trying to give an analogy exactly. Now that friend, one of you will not have the same strength. Does that make sense? One of you will still be stronger than the other. And so if you have to pull bread off, for example, let's say you wanted to share bread and you wanted to pull off the bread, and because you don't want to use knife to cut, so the moment you pull off the bread, you will not get equal sharing of the bread. Usually, just by my own ratification, my own view of it, the one that is stronger is most probably going to pull the biggest side of the bread, isn't it? So that is the same way it happens with the compounds formed covalently. There is a disparity in the share of electrons or in the pool for electron. Okay, now when compounds that have the same electronegativity value are bonded together, they do not have the share of electron is homogeneous, is symmetrical, exactly. But compounds with different electronegativity values or the different power to pull electrons, then there becomes a problem, and that problem is known as polarization. Okay, now it's not a problem, however, but it's just the concept that occur because of differences in electronegativity values of electrons. Now let me give a chemical analogy. So if I have a particular atom A bonding with atom B, now if this will only occur like this if the electronegativity value of A is exactly equal to or very close to electronegativity value of B. But if their electronegativity values were different, such that A was higher, then you are going to see what looks like this, and then B, even though this is still a compound. Does this make sense? So you see that the electrons are spending more time with the atom A, but not with atom B. So this is because this guy has a higher electronegativity value, this guy has a low electronegativity value, or a low pull on electron, a high pull on electron density. They actually pull electron density, not just electrons. So that's why you can see this. The electrons are spending more time with this guy. So usually, non-metals have generally first, metals have low electronegativity value, usually between 0.9 to 1.5. And in fact, the 1.5 is with like the alkali earth metals. Alkali metals have low electronegativity values as low as 0.6, 0.9, 0.89, and all of those. So these guys have this. While non-metals, including hydrogen, they usually have higher electronegativity value, ranging from 2.1 to about 4.5, I think, 4.5, which is 4.1 rather, 4.1, which is the electronegativity value of the most electronegative element on the periodic table is fluorine, while the least electronegative is cesium, right? Now, but my point is the fact that hydrogen has an electronegative value of 2.1, okay? So if I were to form a bond between hydrogen and fluorine, then you definitely are going to be cheating hydrogen in terms of electron density sharing. So what happens is that the electron density will be closer to the fluorine than to hydrogen, because this guy has a higher pool on electron. Now, how do you know what values give you leads to this polarization? Because polarization in that context, in the next video we are going to talk about polarization and the effects, okay? I'll come back to link it down in the description. Okay, but my point is that this 4.1 is very, very greater than this. In fact, it's going to be 2, right? Once the difference in the electronegativity value is less than 0.4, then the polarization will not occur. Does that make sense? That is, they will have a relatively equal pool on electron. I hope that makes sense. So for example, let me give an example. Carbon has the electronegativity value of 2.4 according to the Pauling scale. Okay, Pauling and other scientists came together to create a scale of electronegativity values. So carbon has a electronegativity value of 2.4, while hydrogen has 2.1. If you subtract, you're going to get 0.3, which is not up to 0.4. So when you have a bond between carbon and hydrogen, the electron density is going to be almost equal, or at least equal, or at least almost equal between them. The sharing of electrons is going to be equal or almost equal. Okay. But if you form a bond between hydrogen and fluorine, or carbon and fluorine, then you have created a problem. So there's going to be a polarization of that bond. Polarization means that one is going to enjoy the electron density than the other, okay? And that brings us to what is called formal charges and partial charges. Now, formal charge, you put a formal charge on an ion when it has totally abstracted or totally lost electrons. So that's why we use formal charges only in ionic compounds, where when they ionize, you're going to have this. These are formal charges. But you use partial charges on this, so that if you have HF bond, then what will happen is that this guy will be partially positive. Why? Because it's going to be losing electron density to fluorine. So you are going to have partial negative charges, negative charge. Does this make sense? Okay. So that is that. And this phenomenon will bring us to bond fission or bond cleavage. Bond fission simply means when there is a separation of bonds, okay? And how or why does this happen? This happens because of what? Polarization. Because of polarization. I'm going to explain polarization because I cannot explain polarization now because I will have to talk about its effects, okay? So we are going to explain polarization and its effects. Well, we have about 5 effects that we're going to be explaining in the next video. But for now, let's talk about bond fission. There are 2 types of fission that might occur. Now, this polarization also occurs because of what? Differences in electronegativity values of the atoms attached or atoms forming a compound. Okay, so the first type of bond fission we have is what we call homolysis. or homolytic fission. Homolysis or homolytic fission. Now, the word homo, what does it mean? Homo means what? Equal. Homo means what? Equal. And lysis means splitting. Lysis means splits. So lysis means splitting, okay? So it means that there is equal division. So it means that when there is, first, I've told you that fission or cleavage means what? Division or separation, right, of the atoms. So it means that when there is separation of the atoms, each of them are going to evenly, they are going to get even shares of the electron. They are going to get even shares of the electrons when they divide. Okay? They're going to get even shares of the... And what is formed actually is a free radical. Is a free radical. And this homolysis takes place only in non-polar covalent compounds. Non-polar compounds. For example, we have Cl to Cl, which forms Cl2, right? Now this bond is non-polar. Why is it non-polar? Because chlorine has an electronegativity value of about 3.5. No, 3.5 is that of oxygen. Chlorine is about 2. Is higher than carbon, which is 2.4. So chlorine is going to be about, let's just say 3, can't remember. Then oxygen is 3.5. Okay. So now my point is this, that both of them have electronegativity values of 3. Say 3. Let's say 3. Now it means that they will have equal pull on the electron. So it means that this bond is non-polar. So how does it cleave? So that brings us to the characteristics. Now, this cleavage can only occur in the presence of a catalyst such as UV light. Okay? In the presence of what? UV light. So if this happens, then there's going to be what? Cleavage. What happens is that I've told you before that these bonds, bond refer to 2 electrons, right? Okay, so what happens is this guy, once this bond breaks, this guy is going to get one of the electrons. We represent it with what is called half arrowhead, like this. So this arrowhead is carrying an electron. Does that make sense? So we just draw an half arrowhead. I'm just painting it to show you that there is 1 electron there. Then this other one will also get what? 1 electron. So each of them are going to get one electron. That by the end of the day, we have a free radical that has what? Cl. Okay, so this now becomes very reactive, and you know it is the initiation step for the substitution reaction that occurs with alkanes. This reaction actually precedes it. It is the initiation step. All right, so that is for homolytic fission. Then heterolytic fission. The second one is heterolytic fission or heterolysis. Now, hetero means different, right? Homo, we said same or similar. Lysis, split. Lysis, split, different, right? In this case, there is uneven share. Why is there uneven share of electron? There's uneven share of electron because it first happens between compounds that have unequal polarity. Compounds that have unequal what? Unequal electronegativity. Okay, so for example, if we have a carbon-fluorine bond, carbon has valence electronegativity value of 2.4, fluorine has electronegativity value of 4.1. That is very, very far apart. So the moment we have something like this, then the bond is polar because the electron density this one will be slightly negative charge. That partial charge means that the electron has not been totally abstracted by chlorine, and partial positive charge means it has not totally lost its electron. Only that electron density or electron cloud is closer to the fluorine than the carbon. Okay, once this occurs, so I said that there is uneven share. There is uneven share of electron. Okay, if this bond breaks, if it usually breaks if what we call an organogen comes in. I'll explain this in bond polarization. Organogen. If an organogen approaches this center, what happens is that this bond is going to break, and once it breaks, one electron is going to one of the compounds. So using that C and F, one of the compound is going to get all the electrons. So you have this. So we use full arrowhead. So this guy is going to get all the electrons. So we say that this guy is going to get a positive charge because it has lost electron. Then fluorine is going to get a formal negative charge. A formal negative charge. Does this make sense now? So in organic compounds, this is what gives us ions. We call them organic ions, which are carbanions and carbocations. We are going to talk about this a lot. Carbocations. Okay? So, but keep in mind though that the carbocation that will be formed, this heterolytic fission will only occur if the carbocation that will be formed will be stable. If the carbocation that will be formed will be stable, or the carbanion will be stable. Carbanion is also called carbonium ion. Now the carbocation in this case has to have other components that are going to donate electron density by hyperconjugation, so that this will be stable at the end of the day. So otherwise that fission will not occur. Okay, so it doesn't require catalyst. All that it requires is what? The presence of what? An organogen. It requires the presence of an organogen to happen. Organogen. Organogen can be any such agent that wants to also form bond with another component, maybe the carbocation component. Is that okay? As far as it is attacking, we call it organogen, and there are two types. We have the nucleophiles and the electrophiles. So let's really talk about them. The nucleophile, the word nucleo means what? Nucleus. Phile from the Greek word phileo, which means love, right? So it means that this one loves the what? Nucleus. And what's the charge of the nucleus? The total, the net charge of the nucleus is going to what? Maybe not even net charge, because the only charge there is positive. So the charge of the nucleus is going to what? Positive. So since the charge of the nucleus is positive, it means that this nucleophile loves positive charge or loves positive center, right? So if it loves positive center electrostatically, it means that it's what? A negative charge. So it's going to be a negatively charged organogen. Negatively charged organogen. Negative organogen. Okay, then this guy, an electrophile, is going to be loving electron, right? Love electron. So if he loves electron, electrons are negative charges. So it means that it's going to be what? A positive organogen, positively charged organogen. Does that make sense now? So for them to be attracted to electron, so that's what it means. So that will be it for this video. In the next one, we are going to talk about polarization. Now, I'm already feeling like getting into polarization, but because of time and exhaustion, we're going to pause here and continue on polarization in the next class. I will advise that you see this video to the end, please. This series to the end. We're going to, after polarization, we'll talk about the effects of polarization: inductive, mesomeric, electromeric, mesomeric or resonance, steric, all those effects. We're going to talk about them. Then from there, we graduate to mechanisms of reaction: SN1, SN2, E1, E2. Then we graduate to alkynes, and alkanols, alkanones, carboxylic acids, carboxylates, or alkanoids. Alright, so do well to subscribe to the channel. God will bless you as you do so, and share the video with your friends.